Hi, my name is Yannic Maus, and I will today talk about distributed graph coloring made easy. This is a classic graph algorithms paper, distributed graph algorithms paper. So we're given a communication network, and the objective is to color this network such that adjacent vertices get different colors. And here the number of colors that we want to use is optimally delta plus 1 colors, where delta is the maximum degree of the graph. Note that in this setting, it's very simple to compute such a coloring with a sequential greedy algorithm. But in the distributed setting, the issue is that you're one of these computers in the large network and you don't know what the network looks like. So you just have your own ID and maybe you know that you have one neighbor in the network. And you can talk to the neighbor to learn a bit more about the network. You can talk a bit more, but at some point you need to output your own part of the solution. So for example, your color and blue. And everyone else also has to output their solution. But then there's, of course, some part of the graph which you have not seen and not even heard about. And this setting is formally studied in the local or the contrast model. So here, given such a communication network, it's abstracted as a graph on n nodes, and every node is equipped with a unique ID. So for example, with the IP address. And then these nodes can communicate with each other in discrete synchronous rounds. So in one round, vertex can send a message to each of its neighbors and perform some local computations. The important part here is local computations are unbounded and we do not charge vertices for them. The time complexity is only the number of synchronous rounds. So the initial model that was introduced by Daniel roughly 30 years ago did not have a bound on the message size. And a bit later, people also studied the setting where there are bounds on the message size, namely the congest model, where messages can contain roughly order of log n bits, which is just enough to send a constant number of identifiers. All the results in this paper also hold for the congest model, like upper and lower bounds both hold for the local model and the congest model. But I will not focus on the congest model today so much. So what's known about this problem? In the deterministic setting, if you look at the local model, there was a big breakthrough result a few years ago, 2 years ago, which showed that deterministically this problem can be solved in polylog n rounds if you express the complexity as a function of n, the number of nodes. And with some additional work, we also got this to work in the congest model. This area will not be the topic of today's talk. Instead, today I will talk about the complexity regime, where the complexity is mainly expressed as a function of delta, mainly as a function of the maximum degree. And yeah, now I said it's mainly expressed as a function of delta because there's this ugly, or also beautiful, some say, log star of n term. And this goes back to the first paper in the area which introduced this model. This goes back to a lower bound of Daniel, who showed that to color a ring with a constant number of colors, or you can think of this also as poly delta colors because rings have constant degree, requires log star of n rounds. So this means this log star of n term cannot be avoided. But Daniel also gave an upper bound, which also just uses log star of n rounds. And the downside of this upper bound is that it doesn't compute the delta plus 1 coloring, but only a delta squared or order of delta squared coloring. So this algorithm is really good because its runtime is tight in terms of the lower bound, but it uses many colors. But now, note that you can easily go to a delta plus 1 coloring by just spending one round to reduce one color. Because the vertices of each color class are independent and they just can recolor themselves by picking the color not used by any of the already colored neighbors from the regime 1 to delta plus 1. So Daniel's algorithm gave an order of delta squared plus log star n round algorithm for delta plus 1 color. And people were not happy with this because it's pretty slow. So the setting was studied a lot and there were lots of papers which improved this round complexity, where you first apply Daniel's algorithm and then afterwards you try to reduce the number of colors to get down to a delta plus 1 color. State of the art currently takes square root of delta times log delta rounds. And a few years back, we also showed a lower bound of delta to the 1/3 rounds, but this lower bound does not hold in the original local model, or at least the proof does not work. It's a weak variant of the model in which you cannot count. And interestingly, all of these sublinear and delta algorithms here do not work in this model. What I will talk about today is Lineal's initial algorithm, and actually how the results in this paper relate to this original algorithm by Lineal. Because actually what the main contribution of this paper is that we show that small modifications of Lineal's initial algorithm yield most of these results here, or subroutines that are used in these results. So basically all of this can be subsumed in a variation of Lineal's initial idea. So let's start with Lineal's algorithm. At the core of his algorithm is this one round color reduction procedure. You're given an M coloring, and he shows that you can compute a 100 times delta squared times log M coloring in one round. And then he uses this to come up with this log star round algorithm. You just take your initial ID assignment, you interpret it as a coloring with N colors. You apply this result and you apply it log star and rounds until you get down to a delta squared color. There's a small additional trick here in this last step, because if you would just apply this result up here, you would always have this log M, which would always be a log delta term here. So there's some additional trick in this last step. And this is actually the trick that we will look at now. Basically what we will show, if you have a delta to the 3 coloring, you can go to a order of delta squared coloring. Because a slight modification of this algorithm will result all the results of this paper. So this very simple algorithm is as follows. It goes back to Lineal. It's one round of communication, and the node just selects, and that we will discuss on the next slide. How do nodes do this? Selects a candidate color set, SV. This is the set of colors that the node would like to take. Then you send this set to your neighbors, and then you just pick the color which is in your candidate set, but not in any of the candidate sets of your neighbors. The difficult part here is, of course, to pick the candidate set such that this never becomes empty, that you always have a color to choose from. And this picking such candidate sets was solved by Lineal by the use of polynomials. So what you do is you fix a prime, and for the sake of this talk, let's assume 10 times delta is prime. And then you consider all polynomials of degree 3 over the finite field FQ. And now a node with input color I, so the input color space is delta to the 3 here, just picks one of these polynomials, such that different input colors get different polynomials. And because the number of polynomials here, distinct polynomials, is larger than delta to the 3, this works. And now once every node has this polynomial, you can very easily compute this sets. The set of a node with color I is just going to be the evaluation of its polynomial at all of its points. So you write down the evaluation as x, comma p of x. So these output colors is x, comma p of x lies in the space fq times fq. The output color space will be q squared, so 100 times delta squared. Now the crucial property why this is sufficient to run the Lineal's algorithm is two of these sets can only intersect in at most 3 positions. This is because two polynomials of degree 3, or of degree at most 3, can intersect in at most 3 points. And together with the size of these sets, you get that if you erase all the intersections of all your neighbors, you have at least one color remaining. So the input coloring here provides enough symmetry breaking to assign distinct polynomials to neighboring nodes. This is what you need to know about linear algorithms. Now I want to talk about the results of this paper. And the main message I want to get across here is that we only do a slight variation of this construction. Instead of low intersecting sets, as linear use them, what we construct using polynomials are so-called low intersecting sequences. So we just do the same, but we just evaluate the polynomial and write the evaluation as a sequence. So P0, P1, P2, and so on. And now the property that we get is that two of these sequences intersect in at most 3 positions. And each element of this sequence now lives in FQ, so is of size 10 times delta. And with these sequences, we now come up with a very simple algorithm. So this is an algorithm which computes an order of delta coloring. It computes an FQ coloring in Q rounds, linear in delta. And the algorithm is just as follows. Without communication, and we just have seen how we do this, each node computes such a candidate color sequence. And then in Q iterations, or until you're colored, nodes just try to get colored with one of the colors in their sequence. So they just go through the sequence and try the colors one after the other. And if there's no conflict, no one tries the same color or is already colored with the color that you try. You pick the color and terminate. So the output color space, all of these elements live in FQ, so it's 10 times delta, that's computes the 10 times delta coloring. The question is, why does it terminate, or why is everyone colored in the end? This is because two of these sequences intersect in at most 3 positions. So when you look at 2 neighboring nodes, while both of them are still trying to get colored, you have at most 3 iterations where they try the same color. And once the neighbor has terminated, they stick to their color. So you can interpret them as a constant sequence or also as a constant polynomial. So again, you have at most 3 iterations where you're conflicting with such a neighbor. So in total, you have at most 6 times delta iterations in which you're conflicting. And because the total number of iterations is more, each node has an iteration without a conflict. So this is a very simple algorithm. It has linear and delta runtime to compute an order of delta. And now you can go to a delta plus 1 coloring by spanning another order of delta rounds and just reduce 1 color per round. What we show in the paper is that you can also do a trade-off of Linear's algorithm and this algorithm that I just talked about. You can compute an order of k times delta coloring in delta over k rounds. And my message here is you just use the same algorithm, but you try multiple colors at once. So you take your sequence, and now instead of trying 1 color, you try the next k colors in your sequence. The only technical part here is, okay, if you try k colors, you also need to say, this is the first color I try in this round, the second, and so on. So this is why the color space, output color space, becomes k times delta, because you need to append each color with this index from 0 to k. This is necessary for the proof to go through. But essentially, it's just the same algorithm. And there are more things you can do with this algorithm. So in these papers that I showed previously, what has been an important tool, is also an important tool in other algorithms, are improper colorings. So for example, defective colorings. Here you want to color the graph with fewer colors, so P is usually much smaller than delta. But each color class induces a graph of a small maximum degree. So here this red node here has only 3 neighbors here with the same color. So here the defect is 3. And there's an extension of this, which is a small out degree coloring, which is just the same, But now you also orient the edges in each color class such that you have a small out degree instead of a small degree. So now you can see this node here, it has one edge oriented towards it and two away from it. So its out degree here is 2 in this color. Both of these are important tools in this area and have been used a lot. And a related term here that people have heard about are defective colorings used by environmental in many publications. So why is it important to compute defective colorings and low out degree colorings? Well, they've been extensively used in various results. So I just put 3 citations here. And also, if we look at all these papers that we've seen before, except for 2 of them, all of them use, at least as a subroutine, defective colorings or low out degree colorings. And I won't talk about the defective colorings, but it's very similar. I will just tell you about this out degree coloring. How do you get this? It's the same algorithm as before, but now we want to compute an improper coloring, so you tolerate conflicts. So you take the same algorithm, you compute the sequence, you choose the parameter q differently, and now you iterate through the colors. And when you try a color, you tolerate up to beta conflicts, because that's fine for you. When you pick a color, you just orient the edges towards the conflicts. And now you can see that you can choose these parameters smaller here, because now you're only blocked in an iteration if there are more than beta conflicts. Again, you have 6 times delta conflict with the same reasoning as before in total, these sequences. So you're at most blocked for 6 times delta over beta iterations. And now if this parameter here is chosen larger, then you have an iteration in which you're not blocked and you get the color. It's a very simple algorithm to compute these out degree colors. So for all of these papers, except the first 2, we've seen that we subsume some of the results, or at least some of the intermediate steps in these papers. So let's look at these 2 last papers. These papers study lower and upper bounds for single round algorithms. Very similar to this algorithm that we've seen at the very start. You can just reduce one color in one communication round. And our contribution in this respect is that we precisely characterize what can be done in a single communication round. So for example, if you're given an M coloring to reduce 2 colors, you need your M input coloring to have at least 2 delta plus 2 colors, and so on. And then additionally, we also have some results for ruling sets. So an R ruling set is an independent set of vertices such that every vertex of the graph has a vertex of the independent set in its vicinity, so in distance R. So in this example, for example, in distance 3. Yes. And we also provide, let's not look at the runtime, we provide deterministic algorithms to compute such ruling sets. Instead, let me just close with some open questions, but let me not say anything about this, but just show you the slide. Thank you very much.